Okay, so in 8.2, we're going to be doing tests of one proportion. That's how the sections are going to run through for the rest of chapter 8. 8.2, we look at running through hypothesis tests of a proportion. 8.3, hypothesis tests of the mean. 8.4, hypothesis tests of the standard deviation. It's really the same sort of breakdown that they used in chapter 7 when they went through confidence intervals. They went through with the proportion, they went through with the mean, then they went through with the standard deviation. And one of the reasons we took the entire last class to go through elements of hypothesis testing is the process that we run through is going to be the same for every type of hypothesis test we ever do. So up on the screen right now, I have it for quick reference here, sort of side by side. And one of the things I highly recommend when you go through all of the homework in my stat lab that's going through a hypothesis test, run it through these steps. If you just go run it through these steps on paper and then go back to my stat lab, you're going to find that you pretty much got the answer to everything sitting there ready to go in. So, and also the way that I've typed up the instructions here, part A goes with step 1, part B goes with step 2, part C goes with step 3. So I lay this out to correspond to the steps of hypothesis testing. So I'm going to zoom in, and what you should always do before beginning is read through the directions and then fully read through the question. So our directions, any probabilities or proportions given in decimal form should be rounded to 3 significant digits or as shown on corresponding tables. So on table A2 for the normal distribution, it goes out 4 decimal places. That would be an acceptable way to write that. When you label things, you should be using the correct symbolic labels. If it's a sample mean, it's X bar. If it's a population mean, it's mu. And then when you write up the hypothesis, it should be using the correct symbols. And we do have underlying assumptions, underlying requirements that should be met. So going back to if we're working with means with the central limit theorem, if our sample size is under 30, our original population better be normal. We're working with proportions here. N times P has to be greater than or equal to 5. N times Q would have to be greater than or equal to 5. But that's all stuff that you should do before you run through the process. So now let's take a look at the question itself. In a study of store checkout scanners, 1,234 items were checked for pricing accuracy. 20 items were found to be overcharges, and 1,214 checked items were not overcharges. Use a 0.05 significance level to test the claim that with scanners, 1% of sales are overcharges. And they give us some insight here of where this, 1% came from. So before scanners was used, that was the historic rate for overcharges. And then they finish off with, based on these results, do scanners appear to help customers avoid overcharges? So we don't address that question until we fully run through the hypothesis test. And one of the things that we want to do first is identify the claim. So our claim here is that 1% of sales are overcharges. So if you think about how they track this information, it was an overcharge, it's not an overcharge. That's a categorical variable. We're dealing with a proportion here. Plus, they didn't explicitly say mean or standard deviation. And they claim that 1% are overcharges, that is, proportion is equal to 1%. We also want to go ahead and make a note of what the opposite is. And the opposite of equal to is not equal to. So we can take this back and have that. So when we go to form our hypothesis statement, if it's proportions in the claim, it's proportions in the hypothesis statement. If it's 1% in the claim, it's 1% in the hypothesis statement. And then now we just have to figure out what goes in between them. And the null is easy because it's always, always, always equal in between in the null. And then in the alternate, it's going to be the strict inequality, which in this case is the not equal. And then the little bit extra that I've recommend people do is put the R and the S in there, and then take a look which part of the hypothesis statement looks most like, if not identical, to the claim, and that is the null hypothesis. So what that's actually telling us is when it comes time to write the conclusion with respect to the claim, we're going to talk about whether or not we reject, the R is for reject the claim, that. So that's about 1/3 of our conclusion. Another piece of our conclusion is actually writing what the claim was. That was that with scanners, %1 of sales are overcharges. So we just literally sorry, computer went nuts here for a minute. So we're able to actually go ahead and write the bulk of the conclusion. Actually, we can fill in a lot of the first part. So we either have or we don't have the evidence too. And whether we have the evidence or don't have the evidence, we're going to find that out when we get to part E here, where we either reject or fail to reject the null hypothesis. But we finish writing the hypothesis statement and we have all but one word of our conclusion already done, if you take your time with that. So part B is about identifying the different pieces that we're working with here. And to identify the tail of the test, we look at the inequality in the alternate hypothesis. It's a not equal, this is a two-tail test. They also want us to identify alpha. Alpha is the significance level. And then they also want us to identify all of the given statistics using proper symbols. When we're working with proportions, in addition to sample size, we're always going to need sample size. We're going to need the number of successes. We're going to be using statdisk to do the computation. Statdisk is going to want the number of successes. They may have given us that. They may have given us the sample proportion. So when we go back to the beginning of this, they told us 1,234 items were checked for accuracy. That is the sample size. And then the proportion that they're asking about was overcharges. So X is going to be the number of overcharges. That was 20. So we've got all of our relevant information. Now we can go down to our rule of rejection, which is reject null hypothesis if the p-value is less than or equal to, and again, we never want to write alpha, we want to write the number that is alpha. So at this point, we've got everything that we need to go on over to statdisk and enter this information. So I'm actually going to have to bring up statdisk and switch over the screen. So where we want to go is under analysis, hypothesis testing, and then we get the same list of choices as we had in chapter 7. We're testing proportions and we have one sample. That's what we choose. And then anything, any box that is filled in, that's something that we have to place a value in. Also, we have this pull-down menu. This pull-down menu is about the tail of the test. So which one of these things matches the alternate hypothesis? It is the not equal case. Our significance is alpha. That was 0.05. We don't have to change it. Our claimed proportion, that is the number in the claim, the number in the hypothesis statement, that was 1%. And again, proportions have to be entered in decimal form. Our sample size was 1,234, and our number of overcharges in our sample was 20. So once we get in all the information we have to put in, we can hit evaluate, and we can also hit plot. And I'll go back to that in just a moment here. So what we see in the dialog box is, first off, statdisk is nice enough to tell you what hypothesis you tested. You know, make sure it's the one that you want. Statdisk really wants to be your friend here. It's trying to make sure that you get this correct. Then it does list out what p-hat is. Then there is our test statistic, and it tells us what the test statistic is. We're using a normal distribution. Our test statistic is z. It gives us our critical value or values. It's a two-tailed test, so there's two of them. And then it gives us our p-value. And we're in hypothesis testing, we're going to use p-value to make the decision. We're not going to do the confidence interval approach. By hitting plot, we see that normal distribution. And where the red lines are, those are your critical values. If our test result falls outside in one of those tails, that means that we'd either have a significantly high or significantly low number of successes here, and then we'd make a change from our underlying assumption. And that's exactly what happens here. Our test statistic is 2.19. So we're a little bit over 2 standard deviations away from what we would expect if the true population proportion was 1%. So what I'm going to do now is I'm going to take this information back to our screen here. So our test statistic, and again, you never write test statistic, you write what the proper symbol was, and statdisk will tell you that. And that was 2.19. And if you throw in the third one, that's fine. One of the things I usually tell my classes is however it's rounded on that plot screen, I'm good with you rounding it consistent with that. And then we also want the corresponding p-value. Now I am very purposefully lining up my p-value underneath that because I want to make sure that I'm comparing the right decimal place to the right decimal place. So our p-value was a little bit under 3%. Is 3% less than 5%? Yes, it is. So we said we'd reject the null hypothesis if our p-value was below 0.05. So we do indeed reject the null hypothesis. And when we reject the null hypothesis, we have the evidence. So the way that you'll see it phrased, it'll be, we have sufficient evidence to reject the claim that with scanners, 1% of sales are overcharges. So according to our evidence here, we don't know what the true proportion is, but we've got enough evidence to say that it's not 1% anymore. So our last question here, sort of our interpretation question here, based on these results, do scanners appear to help customers avoid overcharges? Now, we did a two-tail test. One tail would represent a decrease in the percent of overcharges. The other tail represents an increase in the percent of overcharges. Which tail did we end up in? We're positive, we're off to the right. We ended up with a higher percentage of overcharges than what we started off with, the idea that it was 1%. So yeah, there is a difference with scanners than there was keying in things by hand, and it didn't actually make things better. Apparently, it made things worse. So the true proportion appears to have increased. Now, when you get into these interpretation questions, your answers are going to be in English, which means there's all sorts of ways to write the same thing, but that's the general idea behind why it was no. If we were to go back to statdisk, what we do see right there was our sample proportion. Our sample proportion was 1.62%. So we ended up here having a higher percentage of overcharges, and it was a statistically significantly higher percent of overcharges.